So today we are going to actually continue where we left off our discussion in the first one. Okay. So in the last class we talked about state space modeling, and rather we introduced state space modeling, and here we're going to actually continue our discussion on that. All right. So the topic of discussion. So in the last one, we actually learned how to actually do the state space modeling for very simple systems. So here we're going to actually consider slightly complicated systems. So we're going to do the state space modeling for all right. So, and what we exactly mean by slightly complicated systems, we are going to actually learn that. All right. So those who are joining today and missed the last one, I sincerely hope that you actually came here after watching the previous video, because otherwise this class will be pretty much not understandable for you. Okay, all right. And then we're going to talk about, so in the last class also we talked about how we can actually convert a transfer function model to an equivalent state space model, and here we are going to go in the opposite route. We are going to learn a standard way, because I told you in the last class, and we're going to prove it in the next class, that one unique system, so if I am given one unique system that has just one transfer function model, can have, rather will have, infinitely many state space models. Let me repeat. A single system that has a unique transfer function model would have infinitely many state space models. Okay. So, and that way, the problem is that sometimes we are describing the same system by a seemingly different looking state space model. But today we're going to develop a technique in which you can get the same transfer function back from seemingly different state space models. So we are going to learn what is called the state space to transfer function. So we already know how to actually convert transfer function models into state space models, and today we're going to learn how to convert state space models back to transfer function models, right? So that is something we are going to learn. All right. So now let's, I think, get started. All right. So again, during this discussion, if you find something difficult to understand, make sure to ask me. All right. So let's talk about, again, let's continue state space modeling. And this time around, we are going to consider systems that are slightly more complicated, right? All right. So not a problem, I hope. And also, I would kind of assume that you understood what we did in the last one, because we are going to write down state space models directly from the transfer function models. Imagine I have a system. All right. Imagine I have a system and that has this transfer function model. Let's consider a third order system. All right. So, and let's say this is the transfer function model for that. So s cube plus, say, not s cube, maybe 2s cube plus 5s square plus 4, maybe, plus 3s plus 9, and here maybe a 7. All right. All right. So we actually know how to actually construct the state space model, and we learned how to assume state variables, and everything we pretty much understood, right? So we know that the state model, rather let me just to develop the state space model here right away. Okay, so that would be actually slightly better for you to understand. Okay, let's proceed from the very beginning, maybe. All right. So this is the transfer function model. If this is the transfer function model, then this is by definition the ratio of the Laplace transform of the output to that of the input. So we can actually do cross multiply on this and cross multiply on this. So we are going to get something like 2s cube ys plus 5s square xs plus 3s xs, I'm sorry, not xs, ys plus 9ys equal to 7xs. And now this time around, let me just get rid of this 7 and let's make this 1. So this is just the input, right? And again, I told you that let me just use that notation that we use for state space. So u is the input, y is the output, and u is the input. All right, not a problem, I hope. And so this is just us. So from this, if we just apply the inverse Laplace transform, we get the differential equation description of the system. And the differential equation description of the system is this: 2y triple dot plus 5y double dot plus 3y dot plus 9y, and that's equal to u. And remember, this u and y, these are functions of time. So this is the differential equation description of the system, right? So this is the transfer function model. And this is the differential equation description. Ordinary differential equation model. Right? So these are the two models that we actually have right now. So we actually have the differential equation model, and this is the useful one, right? All right. So let's construct the corresponding state space model, and we know we need to assume 3 state variables because it's a third order system. We need to assume the state variables. So assume. So we already have the input in the proper form. The input is given as u. The output is also in the proper form. The output is assumed to be y. So let's assume the state variables, and that would be it. So the state variables are x1, x2, x3, and we also talked about the physical significance of these, right? So if it is describing a mechanical system where y is displacement, then y dot is velocity and y double dot is acceleration, and this is exactly what these state variables are describing. So this is assumed to be y, this is assumed to be y dot, and this is assumed to be y double dot. And we also realize that having 3 state variables for a third order system is sufficient. Similarly, having 4 state variables for a fourth order system is sufficient. So you don't need 4 state variables here, you just need 3 state variables, right? And that will actually convert this third order differential equation into a single first order ordinary differential equation in the matrix form. So that way we would have a standard representation of this. And again, we have discussed all this in the last class. So this is x1, not a problem. So this is y dot. So this is in turn equal to x1 dot because y is assumed to be x1. And this is y double dot. So this is in turn derivative of y dot. So which is derivative of x2, right? So this is something we already understand, I hope. All right. Now our intention is to do this substitution here in the differential equation. Right? So let's do this substitution in the differential equation. So let's bring this differential equation back here and do this substitution. All right. So instead of y, what do I need to write? Instead of y, I need to write x1 because that is the substitution we assumed. Instead of y dot, what do I need to write? x2. Instead of y double dot, what do I need to write? x3, right? And instead of y triple dot, this is like x3 dot because x3 itself is y double dot. Okay, so second derivative of y. So x3 dot would be the third derivative of y. So now we have done the substitution, and this looks like a single ordinary differential equation of order 1. So this is an ordinary differential equation of order 1. So we just converted everything into a first order ordinary differential equation. And if we just take this and bring this here, so let's say this becomes 2x3 dot equals minus 9x1 minus 3x2 minus 5x3 plus u, and divide everything by 2. That gives me x3 dot as equal to minus 9 by 2 x1 minus 3 by 2 x2 minus 5 by 2 x3 plus 1 by 2 u. Now this differential equation along with the two preceding differential equations like these two regarding the derivative of x1 and derivative of x2. Okay, so we also defined the derivative of x1, so x1 dot as x2 literally, and x2 dot as x3. So if we write this down, okay, then what we have essentially is a set of three first order ordinary differential equations. And this set of three first order ordinary differential equation actually is a decomposition of this third order differential equation. So we had a third order differential equation, and using the state space technique, we have decomposed it into three first order ordinary differential equations. So these three equations are individually first order ordinary differential equations, and taken together they are essentially a decomposition of this differential equation, okay, which was a third order differential equation. So this is exactly what we do in the state space model. We, while developing the state space model for an nth order system which is described through an nth order differential equation, we convert that nth order differential equation into n number of first order differential equations, and then we actually combine it in the matrix form. Okay, so we write it this way, like this is x1 dot and this is x2 dot, this is x3 dot. Again, we discussed all these things in our last one. So we want to combine it in the matrix form, and so this is like 0x1 plus 1x2 plus 0x3 plus 0u and so on. So that way this is just simply like this: 0 1 0 0, right? That's x1 dot. Similarly, x2 dot is 0 0 1 0 here. And for the last one, I have minus 9 by 2, minus 3 by 2, and minus 5 by 2. And here I have a half. And that's the differential equation. So that is kind of one differential equation that is describing everything. So here, what we usually do, we assume this is a vector, right? We assume this vector as something like this. We call this vector the state vector. Okay, x1, x2, x3. So that's the state vector, and thus the derivative of the state vector, which is represented this way, is simply x1 dot, x2 dot, x3 dot, right? And thus we can actually write it down using these nomenclature. All right. So this differential equation simply becomes x dot. Notice the underlines. These underlines indicate that these are not just scalar quantities, these are vector quantities. Becomes equal to, this matrix is called matrix A. Okay, this matrix is called matrix A, and again we talked about all these things in the last one. And this matrix is called the matrix B. Okay, so we write it as x dot equals A x plus B u, right? Where A and B are these matrices. Now look at this. Isn't this very similar to writing x dot equal to ax plus bu? Okay, where now I have capital letters here and underlines that indicate that they are vectors or matrices. Okay, but this is very similar to having a differential equation that looks like this, which is a first order ordinary differential equation. And this is also a very similar thing to a first order ordinary differential equation, and that is the intention here. All right. So this is the state equation of the system. Equation describing the dynamics of the system. Okay, right? Yet here we don't yet see the input. We don't yet see the input particularly in this one. Okay, in this equation we don't yet see the output. Sorry, we don't yet see the output. We have the states, so internal behavior, internal dynamics of the system. So once again, to repeat, if this is kind of coming from a mechanical system, then y is probably displacement of something. Then y dot is describing the velocity of that something. Y double dot is describing the acceleration of that something. Now here, as per the state space representation, what is x1? x1 is just y. x2 is just x1 dot, and x3 is x2 dot, which is y double dot. Essentially, x1 describes the position or the displacement, x2 describes the velocity, and x3 describes the acceleration. So these are kind of the internal states of the system, the behavior of the system, right? So these encapsulate the behavior of the system x1, x2, x3, and that's why these are called state variables. The variables that describe the internal state of the system, rather internal states of the system, right? So that's how this equation is known as the state equation. But it is still not yet describing the output, right? It is not yet describing the output. To describe the output, we need to also look at how we have the output here. So the output is y, right? But what is y? Y is just x1. So we have to go back and write it in the matrix form once again. So y is just equal to x1. And if y is just equal to x1, if that is the equation, we have to also write this in the matrix form. So I cannot just write x1, right? So this is the variable x1, x2, x3. That's the state matrix. So this is called the state vector. Okay. This is the vector containing all the states. So this is the state vector, and this is the derivative of the state vector. All right. So in order to write this, just we need something like this, and this describes this adequately. All right. So we have a model that looks like this. So this equation also can be written as simply y equal to cx. This is a C matrix. All right. So this is called the output equation. And these two equations taken together forms the state space model of a system. Remember, this is not a differential equation, this is an algebraic equation. But these two equations taken together forms the state space model of the system. So in other words, we had a system which was described using a particular transfer function. Okay, let's recall that we started with this transfer function model. And from there, we got an equivalent state space model. Okay, and there the state space model was simply this differential equation: x dot is equal to ax plus bu, where a is this, ax plus bu, where b is this, and y is equal to cx, c, right? We also have something called du, but the d is 0 in this one. So this is kind of the state space model of the system that we just described in the transfer function domain. And this model is a very systematic model, and this is very useful in a computer, okay? Because this is so systematic that it is actually, we can actually write computer programs very easily for this to actually be used in a computer. And that is exactly what happened. In earlier days, you did not have computer programs that could deal with transfer function models. In earlier days, we had the computer programs that could deal with state space models, because these are very systematic and easy to write programs for, okay? And that was one of the intentions here, okay? The intention behind developing state space modeling, state space technique, was that it should be very systematic, it should be very algorithmic, which means you should be able to follow a certain process, and that process will lead you to a correct answer. I'm saying one correct answer because there are many, infinitely many correct answers when it comes to, usually when it comes to state space modeling, okay? So that is something we are going to talk about right now, okay? Now let's say, instead of having a 1 here, what if I have something else? What if I have something else? Just hold on. All right, instead of having 1 here, what if I have like something like 7? Okay, just like we did, just like I originally wrote. Okay, so I have a 7 here. Imagine I have a 7 here. So what are the changes I'm gonna see? What are the changes I'm gonna see? I would have a 7 here. So I would have a 7 here, and I would like I have a 7 here, right? Right, not a problem, right? So let me bring this differential equation here, right? Also, let me just bring all this back here, because that will be easy for you to see. All right, so for this thing, for this transfer function model or this ODE model, we have this state space representation, not a problem, right? Now if I have a 7 here, what does it change? We have a 7 here. What is happening really? Really speaking, you see, what is happening is the input is becoming 7 times as much. The input is becoming 7 times as much, right? Right? So previously the input was just U. Yeah, because it was like 1 U, right? And now it has become 7 times as much. So question is, what is the change that I need to accommodate in order to establish that? Previously, if we just convert this directly, like we did in the last class, if we convert this directly, it will simply be a 7 here, okay? If we convert this into a state space model directly, we would see that there is a 7 here, there, and that describes the system adequately without any issue. But is there another way? Is there another way in which you can actually understand this particular system? Let me tell you, there is another way, okay? Let's go back to having this 1 here. Having this 1 here. Now what is this? This is describing a system, right? Not only just a system, this is an LTI system because it has a transfer function model. Okay, right? We can only have transfer function models for linear time invariant systems. Now this principle of linearity will now come into action. Let's see, we have a system, right? Let me just describe this once more so that it is slightly easy to understand. Now we have a system where U is the input, and what is the output? The output is Y, right? That is the description here. The output is Y. If U is the input, the output is Y, right? Now in terms of state variables, the output is simply x1. Output is called x1 because I assumed Y to be equal to x1. Not a difficult thing, right? All right, not a problem. What if I write a 7 here? What if I write a 7 here? That means I have a 7 here and I also have a 7 here, which means the input has now become 7u. The input has become 7 times. Now this is an LTI system. So it's a linear system, first of all, right? So if the input becomes 7 times, what is the result really? If the input becomes 7 times, then what is the result? The result is obviously that the output also becomes 7 times, right? So the output becomes 7y. The output becomes 7y, right? That way, we can now understand something very important about it. We bring this one here and we try to understand something, that this equation was simply like, this is a very complicated way of writing this. I mean, this output equation, okay, this output equation was simply y is equal to x1. That is the output, right? That is the output. Now, what if I have a 7 here? I mean, I could have written a 7 here by doing it from the very scratch, right? Now, once again, if this is 1, this is the final equation. Now, if this is 7, because of the linearity of the system, what happens in that system? Whatever happens in the system, for the linearity of the system, the output also becomes 7 times as much, right? So that is something we can also write. So we can write this as well. And let me tell you, this is the standard way in which you need to write these things. So this is now becoming 7 times x1. All right, 7 times x1. And that way you have kind of a different C matrix here. All right. So when I had 1 here, I had 1 here. Okay. When I had u as the input, y was the output. Not a problem. When now I have 7u as the input, 7y is the output. Obviously because of linearity. That is something we can incorporate here. Right. If the 7u is the input, then the output is 7 times as much. 7 times as much. Right. And thus we can now reconstruct the matrix C here. So there's going to be 7, 0, 0, x vector, which is essentially x1, x2, x3, and which in turns becomes that. So that is also one representation, and this is the representation we would actually rather follow. All right. So this state space model, this A matrix, B matrix, C matrix, and D matrix, they describe the same system as this state space model. This. You see, they are different because I have a 7/2 here and 1 here, and here I have a half here but 7 here. But these two state space models are equivalent. They lead to the same transfer function. So once you understand how to convert state space models to transfer function models, you would learn that these two state space models are not different. They are describing exactly the same system, right? Right? I think understandable, right? So with that being said, if you understood this, again, please ask any question that you might have if you are missing a point or if you don't understand something here. Let me go back and write down 1 here. Okay, so that I have a 1 here. Okay, and now bring this back. Let me bring this back. Bring this calculation back. So let me make this 1. All right, and let me bring this picture as well. All right, so this is u and this is y. Not a problem, right? Now what if I have something like, say, 4s here. I have 4s here in the numerator. So that would indicate that I would have to write 4s here, right? 4s xs. That would make sure that this is not exactly, so just for the moment, let's write x. Okay, let's just write x s. I mean that would be s x s, right? And that would be just the derivative of x, right? That's the ODE model. Sorry, not u. I mean we're writing u. I'm really sorry. So this is u s, and this is the derivative of the input. Okay, u is not unit step necessarily, it's the derivative of the input. Now, previously, look at this once again. If I have u as the input, I get y as the output. Okay, rather, I get x1 as the output, right? So the output is just x1. Okay. Now, what if I differentiate the input? Now, once again, linearity kicks in. Linearity tells me that whatever happens to the input, whatever linear thing happens to the input, that same linear thing will also happen to the output. Now, differentiation is the linear operation. So I differentiated the input. What's going to happen to the output? The output will also get differentiated. So this is going to be the output. If the input is u dot, the output is x1 dot. If the input is u, the output was x1. So if the input is u dot, the output is x1 dot. Not only that, if the input is something like 4, I have 4s here. That means the input is 4u dot rather. If the input is 4u dot, then the output is, so input is 4u dot, then the output is simply 4x1 dot. You see? But we also know that previously we defined x1 dot as x2. That was the definition. We defined x1 dot as x2. So here the output is just 4x2. So speaking of this, we can actually once again remember that if I have just s here, that would indicate that I don't have this equation rather, but the differential equation description, the output equation actually becomes this: y is equal to x2, because the output becomes x1 dot. And that way it can be written in the form of a matrix differential equation that becomes 0, 1, 0 state matrix and 0 u. Now similarly, if I had 4s here, that would make this 4, right? That's how actually, and also I taught you how to look at this differential equation and construct this state space model, right? This 9 is appearing here, this 3 is appearing here, this 5 is appearing here, this 2 is appearing everywhere in the denominator. Okay, I have a 1 here universally because we are using this particular approach here, and whatever comes here, that manipulates this equation here. All right, not a problem, I hope. So once again, let me bring this equation back, bring this differential equation back. And so before I actually bring this differential equation back, let me ask you this. Hold on. Yeah. So let me see. Once again, let me bring this back here. So this is 1. Imagine this is 1. This is 1. This is 1. No problem. All right. So we have realized that if I have s here, that indicates a derivative. Okay. So let me just write down a general expression, right? Let's say this is 13 s square plus 7s plus 4. Okay. All right. So that becomes, if I write down here, that becomes 13 s square us plus 7s us plus 9 us. And obviously the differential equation becomes (13 u double dot plus 7 u dot plus 9u. Okay. Now we can once again take the help of linearity. Try to understand. If the input is u, the output was y, not a problem. If the input is 9u, if the input is 9u, I know the output is, so output was y and this was just x1, right? This was just x1, right? And now if the input is 9u, I know the output is just going to be 9x1 because that is how linearity works, right? Similarly, if I know that if the input is u, the output is x1. If the input is the derivative of u, then the output is also going to be the derivative of whatever the output I had originally. Okay, the original output was x1, so it's going to be the derivative of x1, right? Similarly, if the input is not just u dot but 7u dot, then the output is going to be 7 times as much. So the output is going to be this. All right. In a very similar fashion, if the input is the second derivative of u double dot, then the output is also going to be the second derivative of whatever output I had. So it is going to be x1 double dot, right? x1 is y, so the output was x1 originally if the input was u. Now if the input is the second derivative of u, look at this, then the output is also going to be the second derivative of whatever I had, right? That's also linearity. Now if it is 13 times as much, like 13 u double dot, then that becomes 13 times as much, right? And the beauty of this is that hold on. And now we have so far applied the principle of homogeneity, right? Now let's apply the principle of superposition. What if the input is something like 13 u double dot plus 7 u dot plus 9 u? What if the input is a combination of all these? Then the same combination would appear in the output. That is homogeneity, right? That is homogeneity. Sorry, that is superposition. And the output here is going to be whatever outputs I individually had for them. So x1 double dot plus 7 x1 dot plus 9 x1. So that is going to be the output. If I add these three and send that as an input, then the output will be a sum of these three. That is, all these are because of linearity. And obviously by now you already know that they have special names. What special names? They are known by special names. So the thing is y, this is y equal to 13. Now x1 double dot is already known as x3. x1 dot is already known as x2. And x1 is just x1. So that is the output. So if we have this transfer function, then that becomes the output. So that actually affects the output equation only, right? That only affects the output equation. So let me bring this here and hold on. I think I made a calculational mistake here. It was supposed to be 4u. Okay, the same thing as per what I wrote earlier. So this is going to be 4. Same thing, doesn't matter. If it was actually 9, not a problem. I'm just trying to make different numbers for all of them, so that you can easily see the pattern. Okay, so that you can easily see the pattern. Yeah, that's fine. And I have to write down 4 here as well. Yeah, that's nice. So if I have this, then obviously you see that the output equation obviously changes, and the output equation now becomes here, whatever that is, right? So the output equation becomes 4x1 plus 7x2 plus 13x3. So we could write this as a matrix simply. And that completes that state space model. Now, if you might want to look at a pattern, particular pattern, you see there is a 2 here, and that 2 appears everywhere like this. Is that 2? Is that 2? So the point being, you would be able to, rather you should be able to look at a transfer function model and construct the state space model right away without actually going through much of any hassle. So there is a 5 here. Okay, and that 5 appears here as a -5. Okay. All right. And there is a 3 here, and that appears here. So that this is something again we discovered in the last one. And we have a 9 here. That 9 appears here. Okay, and everything else is just standard. Okay, and what about this 4, 7, and 13? We see that 4, 7, and 13, they are appearing here. So let me use different inks. I don't know. Yeah, that's 4, and that 4 is appearing here. Okay, that's 7. That 7 is appearing here. Okay, and that 13. What ink I'm going to use of that? Maybe this, and that 13 is appearing. And I know that these are not so bright colors, but it will do. All right. So now by looking at a transfer function, you kind of can construct the equivalent state space model. Please let me know if you have any query up to this point. Any query up to this point? And if you don't have any queries up to this point, let me write down another transfer function. All right, let me write down another transfer function. And this time around, the transfer function is 4s cube plus 23 s square plus 13s plus 22 divided by 2s cube plus 5s squared plus 3s plus 9. Now, if you now want to approach this problem like we did earlier, okay, like we did earlier. So if I want to approach this problem like we did earlier, and we would have this part of the model, not a problem. So if that is it, and obviously let me just write down the differential equation similar to this. Then we see that we have a system, of course linear and time invariant system, and instead of all these, if I just had 1, okay, then the output would have been just x1, right? The output would have just been x1, but not, we don't have that. Okay, so if the input is just u, the output is simply x1, right? Now if the input is 22u, the output is 22x1, not a problem. If the input is u dot, then the output is x1 dot, not a problem. If the input is 13u dot, then the output is 13x1 dot. Similarly, if the input is u double dot, not a problem, the output is x1 double dot. If the input is 23u double dot, the output is 23x1 double dot. Right? All these are coming from linearity. Similarly, if the input is u triple dot, the output is x1 triple dot. Now, if this is 4u triple dot, then this is 4. Now, these are all fine. Here we see that this is just 13x2. This is just 23x3. And this is just 4. Now what? x1 triple dot. Let's go back. What is x1 triple dot? I see that x1 is y, so x1 triple dot is x3 triple dot, x3 dot, because x3 itself is y double dot. So x1 triple dot would be x3 dot, because x3 itself is this. So if I write this, then we have a problem. So this is x3 dot. Now we have a problem. What is the problem? The problem is when we want to write down this equation. When we want to write down this equation can only accommodate whatever appears here, right? Because this equation can accommodate like x1, x2 and x3 only, right? Because it has only 3 state variables. So this is the output equation. Okay. So it can only accommodate x1, x2 and x3, but not any derivative of them. Like x3 dot is not accommodated. You cannot accommodate it, right? So when we want to write this down in this way, it becomes a problem, because this term has no place to go in the output equation. This term now does not belong in the output equation because it has one derivative of x3 involved. Okay, and the output equation is an algebraic equation. This is not a differential equation. Okay, so it cannot involve any derivatives whatsoever. So that way, even though this is true, this is exactly true, this is correct, absolutely, but this LTI system, this type of approach is not usable in a state space model, because the output equation now requires a derivative. Okay, the output equation now becomes a differential equation. It can only handle x1, x2, x3. It can only handle the state variables themselves, not the derivatives, like not the derivative forms. And if that is exactly what happens, then now we have to notice something important. We have to notice that this happened because the order of the numerator was equal to the order of the denominator, right? So order of the denominator is 3 and the order of the numerator is also 3. And this sort of shenanigan happened because the order of the numerator became equal to the order of the denominator. Look at all the previous examples. We have tactfully kept the order of the numerator lower than the order of the denominator, right? We have always kept the order of the numerator lower than the order of the denominator. But here we see an example where the order of the numerator is equal to the order of the denominator. And under this scenario, this sort of approach does not work. I mean, of course, this sort of approach works, but with some modification. Now, what kind of modification we need? We need to express this using an idea that would help us convert the numerator in a way that it becomes a differential equation with order where the order of the numerator is lower than the order of the denominator. What am I talking about? I'm talking about this. We can take this and do some sort of a long division on this. We can take this and do some sort of a long division on this. Let me explain what I mean. We are doing some sort of a long division. Okay, how many of you remember long division from your childhood? So we are doing a long division, right? All right, so we are doing a long division. So we are kind of dividing this polynomial with this. This polynomial is going to be divided with this polynomial. All right, let's start the long division. So what if let's start the long division here right now. So of course I see that I have, this is like 2s cube and this I have 4s cube. So comparing these two, I can see that of course I have to write a 2 here. I have to write a 2 here. Okay. So if I write a 2 here, and that actually becomes 4s cube plus 10s square plus 6s plus 18. Now do the subtraction. Okay, if I do the subtraction, I now have 4. Let's do this way. Of course these two will cancel out. That was the objective, right? We reduce one factor by doing this polynomial long division, right? We try to reduce one. So this is becoming 13s square plus 9s plus 4. No, not 9s, 7s. 7s plus 4. And it cannot proceed any further because it is now a higher order polynomial than this. So the end of long division is here right away. Okay, that's the end of the long division. But what have we realized out of this? What is the meaning of all this? The meaning of all this is that this is equal to 2 times this, 2 times this plus this. That's how divisions work. So this is the quotient. Okay, and this is the result of the division, right? Not a problem, I hope. So this is what I divided, and this is what I divided it with. Okay, and this is the quotient of the division. Okay, and this is the remainder of the division. Okay, right? This is the quotient. The result of the division so far. Like this is that, and this is the remainder of the division. Right? So this is exactly what we realized right now. And if I now divide both sides by this, write it down like that. If I write it down like that, so let's bring this once more, copy and paste this here. Let's bring a few more pages. All right, and if I now write it down here, okay, and divide both sides like this by this, so I'm writing this 2s cube plus 5s square plus 3s plus 9. Then this simply becomes 2 divided by that and 2 this divided by that. So 2 divided by 2s cube plus 5s square plus 3s plus 9, and this also becomes 2s cube plus 5s square plus 3s plus 9. So this is actually just equal to 2, and this is plus 13s square plus 7s plus 4 divided by 2s cube plus 5s square plus 3s plus 9. So this is it. Now this is the transfer function for which we wanted to figure out the equivalent state space model. Right? Now what kind of representation is this? This is the parallel representation, right? This is the parallel representation. And now let's try to make use of that. So if U is the input, then it is actually going into two things. It is going into one very simple thing where it is just a multiplier and it is multiplying it by 2, so it's a gain. And we have another system for which this is the transfer function. For which this is the transfer function. And the outputs of these two are combined in a summing block. Okay. Output of these two are combined in a summing block. These are all plus here, and that's the output. Okay, this is exactly what it is describing. So this is U, okay, and this is the output Y. Now let's think about it. We already have seen this system. Look at this system. We already have seen this system where, just in the previous example, this was the previous example. Notice very carefully. This was the example that we have here. And additionally, we have a parallel path that has this very simple system here. So we wanted to construct the state space model of this, and we realized that the state space model can be constructed using this idea now, right? Using this idea. Now forget about this for the moment. Forget that it even exists. Okay. Forget that it even exists. If you forget that completely right now, okay, just forget that it even exists. So imagine it does not even exist. Gone, right? So keep that in mind. And so if this is just 1, then the output is just going to be x1, right? As usual, output is just going to be x1, right? But the input, but here I don't have just 1, right? So I have 4 plus 7s plus 13s squared. So this is exactly going to, what is going to happen to this? Exactly what happened before, right? So if the input is U, I know the output is x1. Similarly, if the input is 4U, I know the output is going to be 4x1. If the input is U dot, I know the output is going to be x1 dot. If the input is 7U dot, because of this, if the input is 7U dot, then the output is going to be 7x1 dot. If the input is U double dot, because of this, the output is going to be x1 double dot. If the input is 13U double dot, the output is going to be 13x1 double dot. Okay, all right. And this is just 4x1, nothing, no changes here. So this is just 7x2, and this is just 13x3. 13x3. And these are all the corresponding inputs at that moment, right? And if I now add these three, just like we did before, so if the input is 13U double dot plus 7U dot plus 4U, the output is going to be a sum of these, this, that is superposition, right? That's going to be 4x1 plus 7x2 plus 13x3. And that is exactly what we had here, 4, 7, 13, right? And so far what we have done, we have discarded this path. Now we actually have this path, right? Now here, what is this path? This is the feed forward path. So this is a feed forward path, which means that this is actually not going through the system per se. Okay, this is the feed forward path. And now if you forget about this completely, I mean, what is the output due to this? But so what is the output due to this? If I forget about this completely, what is the output due to this? This is just twice as much as the input, because this is just a multiplier, this is just a gain. It is just multiplying the input by 2, and that appears as the output. And that is exactly what you have. Y is equal to 2U. Right? Now, when all of this works together, when for this I have Y, the output correspondingly is 2U. When all of this works together, in totality, this is the output. The output for this part was 4x1 plus 7x2 plus 13x3. The output for this part. And the output for this part is 2u. So what is the total output out of all of these? What is the total output? The output out of all these is 4x1 plus 7x2 plus 13x3 plus 2u. Alright? Plus 2u. So this is exactly the total output here. Okay? So I need to write down the output equation, and the output equation simply becomes 4, 7, 13 x plus 2u. Okay, plus 2u. So here, let me go back and let me tell you that this was the system for which we wanted to figure out the corresponding state space model. And let me just bring this one here. This was for this, okay, 13, 7, 4 here for this one. All right. And this is just gonna be 2. So I don't have a 0 here. So this is called the D matrix sometimes. This is called the D matrix. Now here it is a scalar quantity, but here it could also be a matrix D. And that's why previously in our last class, I talked about this and told you that this is called a feed-forward matrix. This describes the direct relation between the, or rather this describes the part of the input that directly appears at the output. Okay, so here that is exactly what happened. The part of the input, this part of the input directly appeared to the output. Okay, not going through the dynamic system here. That's why this is called the feed-forward. Okay, so this is the description. This is that description of this system. I mean, of course, there is nothing similar here except for these portions here. Except for these portions. I mean, let me just copy paste. I mean, except for these, nothing is similar here. All right, and all this came from that long division thing. So now you understand how to properly construct state space models out of transfer function models. Right? If a system has a transfer function model, then it definitely is going to have an equivalent state space model, and this is that equivalent state space model here. Now, as I told you, there are infinitely many state space models describing one single transfer function model, and we are going to actually dive into that in a future class. And let's now give you a general way. Now, of course, if you already have understood the pattern, if you already realize the pattern, you could always go back and construct the transfer function model without any problem. But in general, let's figure out a way in which, in general, we can convert transfer function state space models into transfer function models. Okay. The way we have been doing it so far is known as, has a very special name. It is called the phase variable canonical form. Phase variable canonical form. The word canonical means standard. Okay, it's a phase variable standard form kind of. Okay, so there are many standard forms and then there are many non-standard forms. Okay, so this is one of the canonical forms that we have studied so far, and there are two more canonical forms that we are going to study in the future. Okay, And of course, you can have infinitely many different forms. Those may not be standard forms, but those would be equivalent, absolutely equivalent without any question. It is partially equivalent or what? No. Any system actually has infinitely many state space models. Okay. Any LTI system would have infinitely many state space models describing the same thing. When you convert it back to a transfer function, you would get the same transfer function. Now, what is the advantage? The advantage is that whenever you are designing a particular controller, a particular type of canonical form is better suited when you want to design a controller. When you want to design something called an observer, a particular type of canonical form is more suitable. So depending on what you want to do with your system, you approach the state space model that way. Okay. So that's the phase variable canonical form. Now let's talk about the second part of today's discussion. And here we are going to generalize our way in which you can convert a transfer function model into an equivalent, a state space model into an equivalent transfer function model. So let me write it down. State space to transfer function. Okay, state space to transfer function. All right. So what is the state space model? The state space model is described using this differential equation. X1 dot is equal to AX plus BU. I'm considering a SISO system, single input, single output LTI system. Of course, since I am constructing the transfer function, I also have to assume 0 initial conditions. All right. So I'm not putting underline on U, indicating that it is a scalar quantity. Okay. And corresponding to the output equation is Y, which is C times X plus DU. And both of them are scalar quantities here. So not a problem. Again, just matching the order, and Y is also a scalar quantity. So input is the scalar, output is the scalar. Okay. That's why it's a single input, single output system. Right? That's the state space description of a system. Okay. Right. Now, what is the equivalent transfer function? I told you that if you know matrix A, matrix B, matrix C, matrix D, that's it. You know the system. You know your system without any problem. Right. You know your system. And then now try to convert it into an equivalent transfer function. Right. Remember that X is denoting the states, Y is the output. Right. So let's take this equation. Okay, so let me write down applying Laplace transform on the state equation. So this is the state equation, this is the output equation. Okay, on the state equation, assuming 0 initial conditions. Okay, so if I apply that, then this becomes S axis. Now, what is this thing? What is this axis? Okay, so I told you that X, which is the state variable, is a function of time, of course, and that is just X1, X2, X3. These are all functions of time. So the Laplace transform of that is denoted as Xs, and this is the individual vector of individual Laplace transforms here. So I'm just considering 3. It could be a 4th order system, 5th order system, 2nd order system, doesn't matter. So it's going to be X1s, X2s, X3s, and so on. And just like that, the Laplace transform of the corresponding derivative of Laplace transform of the derivative of this. So if I have this X dot, okay, the derivative of the state vector, so that is just X1 dot, X2 dot, X3 dot, and the corresponding Laplace transform of that is simply the S times individual Laplace transform. So it is going to be S X1 S, S X2 S, S X3 S, and from that you can factor out this s, and thus we have x1, x2, x3. So that is just s times xs. All right. So that is the idea here. That's the rough calculation that you need to remember. So let me just bring it up. Okay, and all right. So this is the equation on which we are applying the Laplace transform. So it becomes s xs. Don't worry, we're going to solve a lot of problems with this. Okay, and then that becomes a xs plus b us. Of course, we are taking the Laplace transform there as well, right? Any problem there? I don't think so, right? All right. So now let's bring it here. Remember that A is a matrix, X is a vector, all that, right? So let's bring it to the left hand side. So if I bring it to the left hand side, then I have S xs minus A xs, and that's equal to B us. Right. Remember these underlines. Whenever I have an underline, it indicates it's either a vector or a matrix. Now, whenever I'm typing it in a computer, or whenever you get in a printed form, you would see that these underlines are not there, but instead they are used bold. We use bold letters. Okay, we use bold letters and write A, B with bold letters. That indicates same thing. Okay, so just keep that in mind. Now, what if I want to factor out x? Okay, what if I want to factor out x? Before I ask you this, let me ask you a very simple question. Okay, let me say I have b minus ab. All these are matrices. Okay, all these are matrices. I want to factor out b out of this. These are matrices. Okay, these are all square matrices. Say this is 3 times 3, this is 3 by 3, this is 3 by 3, all square matrices. Okay, now I want to factor out b. Okay, so I want to write down b here. So something minus a. Is it 1 minus a? Do I write 1 minus a? No, I don't write 1 minus a. I write I minus a. Remember that. Okay, because I is the identity for matrix multiplication, right? So whenever I do matrix multiplication, I is the identity. So it is something like I times b. I is the identity matrix of proper order, right? It's a third order system, so it's a third order identity matrix. Yeah, it's like that. It is like that. So in a very similar fashion, when I factor this out, factor this xs out of this, so this does not just become s, which is a scalar quantity. Instead, it becomes si, and there we have a. Okay, and that equals b us, right? Right, at any step, if you don't understand any of these or some of these, please let me know right now. Now this is a matrix. Okay, this is a matrix. So now if I write xs here, that would indicate that I have to bring this to the right hand side, which means I have to also maintain the order of multiplication. In general, for matrix multiplication, AB in general is not equal to BA. In general, that's not true. So matrix multiplication is not commutative in nature. So I have to preserve that order. So whatever that is, I have to bring it accordingly to the right hand side and maintaining the order. So it was pre-multiplied, so it is going to be pre-multiplied here as well. But the inverse of that. So it's just like bringing a reciprocal of that times b times u. Alright. So that is xs. So that equation is fine with us. And again, I'm going to explain the essence of this equation in a future class. All right, so that's fine, not a problem, I hope. And there, from out of this, we now can apply this in the output equation. Now let's do the same thing. So let's call this equation number 1. And let's say applying Laplace transform on the output equation. Applying Laplace transform on the output equation, and I don't have to assume zero initial conditions because that's not needed. That only comes for the differential equation. Okay. So if I do that, then of course, what was the output equation? That was y equal to cx plus du. It's a very simple algebraic equation, not a problem. So this becomes y equal to vector equal to cx plus d. Remember, u is the input, y is the output. Now that's equation number 2. Now look at this. I have xs. Now x is kind of an intermediate variable here, right? And y is the output, u is the input. So what if I bring this xs out of the first equation and put it on the second equation? So that is exactly what I'm going to do. So putting 1 in 2, we get, what if I do that? I put xs, whatever that is, if I put that, so I have ys, which is the Laplace transform of the output, that becomes c, which is the output matrix, times xs, but xs is known to be this, and this is plus d us. We get this. Now from this, we can actually factor out us, and that becomes c. And if I do that, if I factor that out, this simply becomes, hold on. All right. So here, so this becomes c si minus a whole inverse times b plus d, and this is us, right? And therefore, what is ys by us? If I bring this us to the left hand side, because it's a scalar quantity, I have c si minus a whole inverse, so that's the matrix inverse, times b plus d. And this matrix calculation, that actually gives you the transfer function, because this is by definition is the transfer function. So this equation lets you convert any state space model, or rather any state space model for an LTI system, into an equivalent transfer function. Okay. So again, by dealing with, so you get advantages by dealing with state space models, and we are again discussed all this in the last class. Here, that is the description here. So what I want you to do right now, not right now, as an exercise problem, is that bring one of these problems. Okay, bring one of these problems here. So you already know that this is the state space model for, this is one of the state space models for this transfer function model. Okay, for this transfer function model, this is one of those state space models, right? So let's bring this in as an exercise problem. I will do part of the exercise for you, and the remaining part will have to be done by you. So this is the state space model. Now I have to convert this into an equivalent transfer function. The objective is to convert this into a transfer function model, into its transfer function model. So essentially you want to calculate the transfer function out of that. So you have matrix A, so this is matrix A, this is matrix B, this is matrix C, and this is matrix D. Okay, A is this matrix, B is this vertex, this vector, C is also this vector, and D is 0. Okay, so that is exactly what we have here. All right, so that's A, B, C, D for you. All right, so let's bring them in. So the transfer function. So the transfer function by definition is this, right? Let me once again write it down. All right. Now what is C matrix? C matrix is this. So let's write it down. Make it smaller so that everything fits ultimately. All right, that's C matrix for you. Now we have Si minus A whole inverse. Now let's put the brackets here. Now what is Si? Now what is I? I is the identity matrix of order 3 because it's a third order system. Okay. I is the identity matrix of order 3 because it's a third order system. So it is just gonna be simply 1, 1, 1, and everywhere else it is 0, right? Only the principal diagonal is 1. Now, of course, I am writing S here, which means I am multiplying that with the scalar quantity S, which means that these ones are essentially becoming S. So that's S. So that's Si. Minus A, obviously I have the A matrix. What is the A matrix? That's 0, 1, 0, 0, 0, 1, and it was minus 9 by 2, minus 3 by 2, minus 5 by 2. Minus 9 by 2, minus 3 by 2, minus 5 by 2. All right. And the matrix inverse of this. So you want a matrix inverse of this. And then multiply that with matrix B. So Si minus A whole inverse, and then multiply that with matrix B. So that completes that mojo. And obviously D is 0. Okay. D is 0 because here we see D is 0. So I don't write anything plus here. Alright, so the big task here is to invert this matrix. The most complicated task is to invert this matrix. Okay. So I have here 4, 7, 13. And before I even imagine inverting that, let me just write it down properly. So this is going to be S and then obviously minus 1 and then obviously 0, then 0, S minus 1, and then I have 9 by 2, I have 3 by 2, and then I have S minus 5 by 2. Take the inverse and complete the rest of the multiplication. And once you complete that, you would get the final result here. You would get the final result. All right. So now, question is: do you have any confusion? Do you have any question regarding this result? So this is the objective. I mean, you have to now do. You have to now take the inverse of this matrix. Okay. Matrix inverse. Okay. There is no Laplace transform involved. Laplace inverse involved here. Just the matrix inverse. Okay. Take the matrix inverse of this and complete the multiplication. You would end up with the transfer function, with this transfer function. This one, you would see. So that is the objective. Will you be able to do this by yourself? So will you be able to continue from here? I asked you a question. I hope you will be able to continue from here, right? And if you have any query regarding what we have discussed so far, and please, before coming to the next class, I mean, please go through the previous class. I know some of you actually missed the first lecture on state space. Okay, so please go through that lecture first. Okay. In any case, will you be able to continue from here and figure out the transfer function? And if you have any query, feel free to ask at this point right now. Okay, have you understood? Did you understand what I have talked about in today's class? Because there is a lot. We discussed a lot of things. All right, so did you understand what we discussed in today's class? Please confirm that. All right, only one of you is saying that you will try. All right, it's not a very difficult calculation, right? A calculation is something you did in your school levels as well. In any case, I hope you understood what we discussed in today's class, and I will see you tomorrow with our physical lab there. All right. Once again, thank you very much.